So, so before we dive into convolutional neural networks, and by the way, this chapter was inspired and built upon the book of Understanding Deep Learning by Simon Prince. So special thanks to all co-authors who contributed to this book. So before we dive into convolutional neural networks, I would like to cover two important properties of a network. And we've already mentioned one in the previous video. So the first one is invariance. So invariance, and the second one is equivariance, okay? So what is invariance? Invariance basically is when we think about, it applies to the input, okay, and equivariance is a property that the mapping function needs to satisfy. So here, as I mentioned, for invariance, we think about the input image. So we say X is invariant to transformation if f of t of x is equal to f of x, which means here that if I take the image of a tree, and I transform the tree. So I transform the image by translating the tree. So this is the translated image. Let's call it t of x. And when I apply, for example, let's say f of x is equal to y here is a label tree that takes a particular value. For example, let's say this value is 4, okay? And then if I learn the network or apply the network to the transformed image, which is t of x, right? The translated tree, then we should get exactly f of x, which is y, which is 3, okay? So in this case, we say that x is invariant, okay, to the transformation t of x. So this is what it means. So x is actually invariant here. Now for the equivariance, we look at the output. So a function f, the mapping f itself, which is the network. So the network is equivariant, or here you can think about it also as the mapping weights. So this is the network, or the learned mapping, okay, or the mapping f of an image x is equivariant to a transformation t of x if f of t of x is equal to t of f of x. So let's think a little bit about that. So first, the rule of equivariance, it is applied to the f, the mapping itself. So here what this tells us is that if I take the image, so let's take the original image here. So I'm going to copy paste, okay, copy, duplicate. So this is my image of the tree. And then what happened is that right here, I translated the tree. So here there is a transformation. Okay, so I applied a t here. I transformed the image. And on the other hand, this is the output data. The output is a segmentation of the tree. So I'm segmenting the tree. So I'm going to duplicate it. So here we have the segmentation of the input image, and we have the segmentation of the transformed image, which should be translated, all right? So what this equivariance is telling us is that if I take the output mask, okay, or the output of f of t of x, which is this one, okay? So this is a transformed image. So I'm applying f to t of x, to the transformed image. It should be equal to the transformed, basically, f of x. So what does it mean, the transformed f of x? It means I apply the transformation to f of x, and I get the same. So this is f of x. So here I am applying the transformation. If I transform the segmented image, if I transform the segmented or output image, we will get exactly the same image as applying, the mapping to actually the transformed image itself. So the pathways go like this. So one pathway, basically apply the transformation to the output, which is, this one. And if we apply the transformation to the output, we're going to get this image. So this is our output image. So right here, I'm going to put it in this color. Or you can take a different path, which is transform the image first. So I'm taking this image and I'm transforming it T of X. So I'm getting T of X right here. So this is my T of X. And then after that, I'm just applying F to T of X, and I get exactly the same image. So what this tells us that F, okay, of an image X is actually equivariant to the transformation T. So here we applied T differently. Here we applied it to the output space, and here we applied it to the input space. So these are two different things, but they are equivariant. We get exactly the same output over there. All right. So this is these are two nice properties that we wish that the network would satisfy. So let's write these down. So the first one is the invariance of the input with respect to transformations. So if we transform here, okay, and the equivariance of the learned mapping with respect to a transformation T also that we have over there. Okay, cool. Now let's look at these examples. So we have more examples, but before that, maybe we can see how we can get these properties to be satisfied in our network. So invariance and equivariance properties. So first, the way we can implement this is we can use augmentation as brute force approach to learn these properties, which means you take an image, right? And if you have this image, you can rotate it. You can rotate the tree. You can translate the tree, right? And you can do multiple things. So this is what we call augmentation. So you apply different transformations to the image, and after you transform the image, you're going to get new images. And by applying, so here actually it's the other way around. So we took this as the original. So transformation T1, transformation T2, okay? And we have transformed these images. So this is what we call augmentation. All right, image or data augmentation. So data augmentation can partially solve this problem. It's called a brute force kind of approach. So you're trying to make or force the network to learn patterns or to depict patterns of a tree, or to interpret a tree independently or invariantly to its transformed versions. Okay, so in this way, the network will look at different kind of rotations and transformations, and because it's trained on such data, it will learn to extract patterns that are not dependent on the rotations. Because remember, the shared weights, we're learning the same mapping. So now we're learning the same mapping that will not change with the with the rotation or transformation of the image. So hopefully, we're gonna get some invariance properties there. So another thing is even better. So instead of kind of playing with the data, you can play with the network. So here, the first solution is basically data oriented, and here it's network oriented, which means we will try to design a network that inherently satisfies these properties, so invariant and equivariant. So what we will do here, so basically we want our network to have these properties, which means F will be equivariant to transformations, so which is the network, the full network model to transformations, geometric transformations. So we're going to add the word geometric here. Geometric transformations, and we want X to be the input to be also invariant to transformations, and this will also can happen in the middle layer. So if you have like your network like this, we want this to be also invariant, right? So, you know, you can apply these properties everywhere, not only in the input layer. So there are things that you can satisfy all along your learning when you go, you know, through all the layers of the network. As we have seen, you can make your network deeper and deeper, and this propagates throughout the whole network, okay? So these are two properties, and for example, we will see later pooling. So pooling actually induces this partial invariance to translation. So when you pool, you know, like images, you're teaching the network how to you know, recognize translated versions. So when you do pooling, somehow you are inherently translating the image, shifting it, and with that kind of shifting, you're creating this sort of invariance in the learned hidden layers of your network, okay, or units. So yeah, so these are two nice properties, and here is an example also from the book chapter. So in this example, in chapter 10, in the first one, so we see different examples of invariance and equivariance to particularly translation, okay? So A and B here, an image, so this is an image classification goal. So we want to categorize both these images as mountain, regardless of the horizontal shift that has occurred. So there is a horizontal shift, and you can see the shift has happened right here. So horizontally, we slightly shifted the image over there. So you can see that this point was right here, and now it's right there. So there is a sort of a shifting that happened to the image, okay? So we shifted it, and what we want is basically to, we want the network to recognize these two as the same thing as a mountain, although it has been shifted horizontally. So in other words, we require the network prediction to be invariant to translation. So we want the network prediction, the final prediction, to be invariant to translation. So which means the final prediction will not be affected by translation. And this is, you know, f of t of x is equal to f of x, which is the prediction, okay? So C and D, if you look at C and D, so in C and D, it's a semantic segmentation task. So the goal is to associate a label with each pixel. So we want to label, for example, here, you know, the chairs right here, we want to label them as blue. You have the table is green. So you want to color basically based on the object, and this is a semantic segmentation example, okay? So EF right here. So when the input image is translated, so we translated the input image also, we want the output, the colored overlay, to translate accordingly. So which means when you do image translation, so here you can see that this has disappeared, right? So we translated the image. So when you translate the image, you want the output to be also translated. And this requires the output to be equivariant with respect to the translation. Okay, so here, this is exactly what we explained earlier. So for equivariance, you want the f of t to be equal to t of f. And if you translate the image, the output should translate. So f of t of x would be equal to t of f of x. Okay, cool. So now there's actually a small exercise, but I need to kind of, I forgot to hide the solution. So let me just do it right here quickly. So what I want you guys is basically to verify this. So you can take a few minutes to show that the operation, which is, you know, the translation here, okay, is equivariant with respect to the translation. The operation here is the convolution, all right? So if you take, for example, a convolution, so if you look at convolution, you have f, you can involve, you know, x by w, so you can involve x by w. So you're gonna have x1 w1 plus x2, w2, etc. You can use different indexing plus, for example, wn. And X here is the original image, right, patch here. And the kernel is, for example, 3 by 3. So this is W, and this is the big X. And then you're doing a convolution, and it's an element-wise multiplication, and then you sum. It's a weighted sum. So this is actually very simple. And here what you can show is that the operation, the convolution is actually equivariant with respect to translation. So what does that tell us? So it tells us that basically we have endowed the network with an operation, okay, that allows us to satisfy this equivariance, at least with respect to translation, which is a nice property, which means if we use convolutional neural networks, we use convolutions in networks, as we have seen here in this example, we convolve by these multiple kernels, right? So we show that inherently we have enabled the network to be invariant to translations because of the operation that we have introduced, which is a very nice property to stipulate in a neural network, okay? So you guys can take, if you 1 minute to write this down or express it, or just think about it, and then I'll show you the solution in a bit. So let's look at the solution together. Actually, it's very simple. You can formalize it mathematically the way you want, but here, let me reveal it to you. So basically what we have here is first, we transform the image. So when we transform the image, we translate it. So this is a translated pixel. So the index here is being translated by tau. Okay, so all pixels are shifted. The positions are xi and its neighbors, xi minus 1 plus 1. So we have 3, for example, here it's very simple. It's 3 elements. So imagine we have, so if you write it right here, so this is actually a very simple example, xi minus 1, xi, and xi plus 1. And then we have the weights, the learned weights, W1, W2, W3. This is one-dimensional convolution. And we do a translation here of by tau. So this will add a tau to all these pixels. So pixel indices. So what happens here is that we have a translated, image, and we multiply it by W1, and you can see easily. So once you do that, it's exactly the same. So it gives us, the fi plus tau applied to x, which means as if we have transformed, the output image. Okay, so it's the output that has been actually translated, and this part right here is, t of f of I. So you can write both, and you can see it's exactly the same thanks to this multiplication. So basically, you guys can think about it. First, you apply the transformation, and then you translate, or you translate, then you apply the transformation, and it gets you exactly the same things. Okay, so that's the equivariance here. So actually, it's too simple. All right, so now we're gonna, after we covered these two beautiful properties, network invariance and equivariance, at least we define them and we understand what they mean and what they stipulate in the network and the input or intermediate layers of the network. Now we're going